Hey everybody, here is their next type of volume calculation. It's called volume by washer method. So let's do a quick little review. In the last set of problems we were working on were volume by disks. So if I had some kind of a function and I was rotating some interval around, let's say, the x-axis, I draw a rectangle that's perpendicular to the x-axis, labeled that dx, and that coordinate had a y value and an x value. And we said that the volume of that region, if you spun it around, was the sum of all of the little disks that would be formed by spinning it around. So that was pi r squared h is the volume of a little cylinder or a disk. So pi, summing them all up, r, the radius of that disk, in this case is going to be x, or the function. So I'm just going to say radius in general squared and dx or dy. Those are general formula. And we spun it around the x-axis, the y-axis, and other axes as well. But now what happens if I get a situation where the actual region that's bounded doesn't actually touch the axis of rotation? Notice this rectangle always sat on the axis of rotation. Well, what if I wanted to take two functions here and the region that's enclosed by them, and I want to spin this around the x-axis? So make myself a little rectangle, and now I want to spin this rectangle around the x-axis in 3 dimensions. And what would that wind up forming? Well, I take this outer one and spin it around, and this inner one and spin it around. And I'm not the greatest drawer here, but I wind up getting like a disc, but with a hole in it. So that disc with a hole in it, we call it a washer. You know, like nuts and bolts, a washer, where it's basically a disc with a hole cut through the middle of it. Well, if you think about it, how am I going to find the volume of that? Well, it is basically a cylinder, so pi r squared h, but it's missing a little cylinder inside of there. So if anything, I should be thinking about this as maybe a difference of cylinders. So my volume is going to be, again, I'm going to be with some interval from A to B. And then so I have this outer disk, which is the entire disk itself. Well, that's going to be, pi times the radius. And I'm going to use a big R for the big radius. And that's going to be the radius going all the way from the x-axis up to the top of that rectangle. That's big R. And so it's going to be pi big R squared dx, or dy. In this case, it's a dx, so width of dx, minus the inner little hole. I want to subtract out the hole. Well, that's going to be another integral from A to B of pi and the little radius that just goes from here to here. And that would then little r squared dx. And so really, in essence, we have a difference of disks. And the difference of disks becomes this shape, which we call a washer. Well, notice these are both on the same interval, so therefore I can write it as one integral. So pi a to b of big R squared, big radius squared, outer cylinder, minus little r squared, inner cylinder, dx, or dy. In this case, it was dx. So a general formula, volume, is going to be pi a to b of big R squared minus little r squared, dx or dy. And in this case, we still are, my rectangles are perpendicular to the axis of rotation. And you might want to put this, pause maybe for a minute, and put this on your foldable. Again, this is not a topic that is on the 2020 exam, but it will be next year for those of you joining me in BC. It's definitely on there. Now you might wonder, okay, if both disk and washer, the rectangle has to be perpendicular to the axis of rotation. Well, what if I made a rectangle horizontal, or sorry, parallel to the axis of rotation? If I spun it around this way, we wind up getting a method called cylindrical shells. And I'll show you that sometime. But you actually can get away with disks and washers on the AP exam and not have to know cylindrical shells. But you probably should know it, and we'll talk about that probably next year in BC. Okay, so let's take a look. Let's do an example here. So I've got a region, and in fact, it's the region that I dealt with up above, of y equals x squared and y equals 2x. That region bounded between those two curves, and I want to rotate that about the x-axis. So here's my y equals 2x, y equals x squared. Probably need to know that point of intersection. We'll do some of this by hand. Always set equations equal to each other. Oops, set them equal to each other so you can see them first. Equals 2x, so x squared minus 2x equals 0. Factor out an x. So it looks like I get 0 and 2. And again, I'm going to do my rectangle going perpendicular to the axis of rotation, and this has a width of dx, so I know my integral is going to be in terms of dx. And I know I'm going to be going from 0 to 2. So now what I need to do is to figure out what big R and little r squared are. Well, big R goes from the axis of rotation all the way to the top of the rectangle. This is going to be that outer disk, the full disk itself. And if I spin that around, well, what is this distance from here to here? Well, think about how we've labeled these things before. Well, this distance from this point to where the rectangle touches, that's x, and this distance down here is y. So therefore, big R is just y. This distance from here to here, that y value. But it's the y value on the linear function. So since everything's in terms of x, I'm going to write what y is in terms of x, and y is 2x. So therefore, big R is simply just the value of the function at the individual x values. That's how big that radius is. Well, right there, if I calculate this right now, I would find the volume of the region spun around if I took this linear function and spun it all the way around, which really is just a cone. So this would give me the volume of the cone that I would then spin around. But I want to subtract out the inner part. Well, the inner part is then based upon the little r, or the little radius. Well, little r is also a y value, but it's a y value on the quadratic function. So it too is y, but it's the other y function, which is x squared. So pi little r squared will give me my inner volume. And I'm subtracting the 2. Well, if I clean this up just a little bit, 0 to 2, so that's 4x squared minus x to the 4th dx. And this one's an easy one to differentiate. So 4/3 x cubed minus 1/5 x to the 5th. And I did this one a little bit earlier, but you can punch it into your calculator too. I got 64/15 pi. Now, that is a volume. That's units cubed. But what is it? What is it the volume of? Remember, we said if we took this region and spun it around the x-axis, well, what's it going to look like? So I got this kind of shape. I'm going to spin it around the x-axis. So it's going to look something like this. But remember, I'm just seeing the outside of it. So really what I have is the outside of it really looks like a cone. But on the inside, we've removed all of this empty space inside of here. So really this volume, typically sometimes people accidentally think that it's the volume of what's filling up inside of here. No, this is the actual volume of the material it would take to make this region if I spun it around. So it is a hollow shape that looks like a cone on the outside, but if you peek inside, the sides would be kind of curving inwards on each other. So it is actually the volume of the material it takes to make that shape. So really, if anything, what I like to do sometimes, because on the outside it looks like a cone, but then I'll use dotted lines to show what the inside region looks like. So really kind of fascinating that again, I think this is a pretty simple antiderivative and integral to evaluate, but it's finding such a complex kind of a shape. So that's pretty kind of awesome. Let's take a look at another one here. So now let's take this same region, but let's spin it around the y-axis. So I got my parabola, I got my linear, and now I want to spin it around the y-axis. So remember, we got to be perpendicular to the axis of rotation. So there's my little rectangle, and I'm going to spin around. It's got a width of a dy, so I already know to start this out. And I'm going to have a dy. And notice this rectangle is not touching the axis of rotation, so therefore I'm using another washer method. It's going to be a difference of volumes. So first of all, let's maybe figure out what this point of intersection was. That was 2 up above, but 2 times 2 or 2 squared, because it's touching both. That equals 4. So I'm going to 0 to 4. Differential is in terms of y, my interval is in terms of y, and now my radii have to be in terms of y. So let's draw them in. Big R goes all the way out there. Well, what would we label this earlier as? Well, big R, that point, remember we would typically label that x and this is y because it's a coordinate on this curve. Well, that's just x. But notice everything's got to be in terms of y. So this is touching the parabola. Well, if y equals x squared, then that means x equals the square root of y. That's my big R. So big R, is the square root of y squared. Well, little r is going to come in down to the bottom of the rectangle, and that's going to touch the linear function. So that's my little r. Well, that distance from here to here is a horizontal distance. That's also an x value, but it's the x value of the linear function. And the x value of the linear function is a half of y, or y over 2. Well, big R squared minus little r squared, difference of volumes. Remember, this is really a pi r squared minus a pi r squared. It's a difference of volumes. Maybe clean this up just a little bit. So that's y. This is y squared over 4. And if I antiderive, y squared over 2 minus y cubed over 12 from 0 to 4. And in the end, again, I used my calculator, but you can check it. I got 8/3 pi. Now, wait a second. Why don't I get the same volumes? Isn't it the same region, just spun around a different way? Well, if you look carefully, this shape, if I spun this region around the y-axis, what's the outside going to look like? Well, the outside is going to look like a bowl. But what's happening on the inside? Well, on the inside, I'm taking out this kind of linear, it's got linear sides inside if I peeked in. So it's really like a bowl, but then with a cone taken out. And again, this calculation is actually the volume of the material it would take to actually make this bowl. Again, I could fill this bowl up with water or something. I am actually calculating the volume of the material of the object itself, not the volume of the material in the bowl itself. So really, again, kind of fascinating way with just a very simple calculation.
I didn't get that. Could you try again?
Thanks, Siri. All right.
No problem.
Let's take a look at the same region, but let's spin it around a different axis. See what happens here, because this gets a little bit trickier. This is about as tricky as it's going to get, I think. So we're going to take y equals x squared and y equals 2x. And I'm going to spin that around x equals 2. Well, here's 2 right here. That was my point of intersection of those two curves. And so I'm going to be spinning around this axis right here. So here's my, I should have made this a little bit bigger. Here's my rectangle perpendicular to the axis of rotation. And now, so I'm going to have a dy. So I know my volume is going to be pi, and it's going to have a dy at the end. And I'm going to be going, these are y values, so I'm going to be going from 0 up to 4. So those need to be y values. So the question is, what's the radii this time? All right, so if I go to make my radii this time, now my radii are coming from the axis of rotation. So this is my radii coming, my big R, coming out this way. Big R is from here to here. Well, let's do our other labeling. This distance here to here, we used to call, or had called it X in my Washoe method. This distance down is Y. So no matter where this rectangle is inside of here, I can always say that, I'm going to write this up above, that X plus big R must always equal 2. The distance from the y-axis to that vertical line 2. So therefore, big R is always 2 minus x. But the function's in terms of y, or the integral is in terms of y. So therefore, I've got to write this x. Well, which function am I touching? I'm touching the linear one. And x is equal to half of y. So therefore, big R is 2 minus half of y. That's big R. So what's little r? Well, the nice thing is once you figure out big R, little r is pretty close to being the same. Here's little r, the little radius. Again, I'm spinning this around this axis. So little r is from here to the bottom. That distance across touching where the rectangle touches the curve, that we call it x again. So therefore, x plus little r, that distance plus the distance of r must always equal 2 as well. And what you see is that these two radii look pretty similar. The only difference is this one's now touching the quadratic, and the quadratic x value is the square root of y. And so there's big R squared minus little r squared. I would take a second and punch it into my calculator to see what I get. In the end, check to see if you get the same thing. I just did it, I actually typed the whole integral. I didn't even antidifferentiate it because I would maybe have to use either a chain rule antiderivative would work for this one, not for this one, because my dy, my chain rule, I don't have another y value. I'd have to actually expand this, but I get 8/3 pi. Again, that is the volume of the material itself. What's this shape look like? Well, the outside's going to look like a cone, but on the inside, it's going to have that curvy. Hey, wait a second, that kind of sounded familiar. That's that same shape that I had on the other side. And if you check, I think it has the same volume. It has the same dimensions, just spun around a different axes. All right, let's take a look at one more. Same region, but now rotated around a different line. So y equals x squared, y equals 2x. This was 2, and that's 4. And now I want to spin it around y equals 4, this line. So here's my rectangle with a width of dx. Let me zoom in a little bit here. And I am going to draw, let me get my integral started. Now I'm in terms of x, so this gets a dx. It's always going to be big R squared minus little r squared. And since that's in terms of x, my interval needs to be in terms of x. So I'm going from 0 to 2. Well, let's draw in big R. Big R goes from the axis of rotation down to here. That's big R, because I'm going to spin this up around this way. Well, this distance from here to here, we would call y, the y value of the points on the parabola. So therefore, I can make a statement that big R plus y must always equal 4. Big R plus y equals 4, so therefore big R is 4 minus y. And I'm touching the parabola, and what do the y values equal? Well, they equal x squared. Now, did I have to change that to x squared? Yep, because this has a dx. And so little r is going to go from here to here. And that distance where the top of the rectangle touches, that's going to be a y value. Again, over to here would be an x value, but I'm not going that direction. So little r plus y equals 4, or 4 minus y, or 4 minus 2x, because it's touching the linear function. And now I can set up big R squared minus little r squared. And can punch that into your calculator too and check that, and I got 32/5 pi, which is a little different than the other one because we were spinning it around this line of 4. So there you go. 4 examples of Washer method. Again, in the end, Washer method is simply just a difference of volumes. It's just a difference of volumes, an outer volume minus an inner volume. So you should be able to pretty easily do these ones that are rotated around the x or the y axes. The ones that rotate around other axes get a little tricky. So try the next couple and then check your solutions with my solutions online. And see me in office hours if you have any questions. See you guys.